Good afternoon, everyone. Today I'll be presenting the Exploring Intermediate Representation for Monocular Vehicle Pose Estimation paper from CVPR 2021. Let's get started. So the 3D properties of the surrounding world, especially cars, are important for autonomous travel to detect, like to do position estimation and prediction, or for anomaly behavior detection and other things. And right now, most of the methods, they use LiDAR or stereo camera to get better prediction for 3D world. And the benefit of these kind of sensors are they work with 3D data, and then they can benefit from multi-view geometry. But usually the LiDARs are much higher in cost, and the stereo cameras, they have some they are very complex to work with. So with this in mind, the RGB image detection of 3D information from RGB image is much more better than those two, and because of cost effectiveness. And then also when we have some good model for RGB image, we can use it with other methods through sensor fusion, and we can benefit other methods. But when we use only RGB image, we have some problems, like we don't have the depth information or other geometric cues. But luckily, with the advancement of deep learning, the depth information is almost solved. So there is not that much problem with this. But the problem with current pose estimation from RGB image is that they don't focus on intermediary results. So what they do is take image as an input, and then they output the pose information. And what happens in between is almost like a black box. So they ask in this paper that can a neural network extract explicit geometric quantities from RGB image and use them for monocular vehicle pose estimations. So they get their motivation from the representation framework for vision. This is very old work actually. I saw the paper, but I didn't understand exactly. But the idea here is that in between of the prediction, they do a 2.5D detection and then convert those into 3D. So there is some intermediary work in between. And another motivation comes from the two-stage human pose estimation. And they recognize the value of learning and in intermediate representation between the pixel input, which is RGB image, and 3D pose information, which is output. So this two-stage human pose estimation, they do some work to learn the intermediary representation. And also additionally, the benefits, they have some benefits to this. And they are like the intermediary geometric representation are easier for humans to comprehend, and the mapping from them to 3D pose is easy to learn, and just few layers of neural network would suffice to get them. And also they are easier to debug when you are implementing them on some safety critical application. So to this end, this paper proposed a novel vehicle orientation estimation approach featuring learning intermediate geometric representation, also known as IGRs. And they achieve this by defining the set of RGRs based on the existing ground truths without any extra manual annotation. So they first define some intermediate geometric representation from existing ground truths, so that they don't do any extra manual annotation. And then they design a GONET model, which the task of this GONET is to regress IGRs only. And also they propose a loss function for self-supervised learning based on the prior knowledge from projective invariance. We talk about this in deep later. And so some related works. So for deep learning based 3D object detection, the aim of these methods are to learn a mapping from sensor input to instant attributes such as 3D orientation or to these 3D locations. And these methods can be divided into three: LiDAR-based, RGB-based, or hybrid. So for deep learning-based 3D object detection, many of them works like in multitask architecture. So like they have the backbone for feature extraction, and they had the estimation head that they get 3D parameters from. And almost in all of them, they had very similar design for the head. So in this paper, they present a dedicated module for predicting the 3D information, which make it different from this model, previous models. And also for pose estimation in 3D object detection system. And the aim of this is to recover the instant orientation. And there is usually two types of the methods: learning-based methods. So they learn a function from pixel to orientation. And then they just do the discrete pose classification or continuous regression to get the 3D information. But in this paper, the method that they propose is it promotes learning explicit IGRs. And then later the model can be reasoned in geometric space, which enables the model to directly estimate global pose and camera coordinate system. Okay, we get back to this later. And the different type of pose estimation are optimization-based method. They first extract 2D evidence from RGB image and then feed 3D models to the evidence for pose estimation. For example, like the 2D evidence can be the detecting 2D key points, and then you can project the detected key points from the 3D model onto the image, and you can do the optimization between the projected and detected key points to get the accurate pose information. So this is optimization-based method. So here is what they propose. So this is the architecture of the EGONET. In the upper part, the model detects the object, and in the lower part, the EGONET module, its sole objective is to detect the 3D information, pose information, and then when you combine it with a detected object from above, you can get much better 3D orientation for each detected objects. And also it's in the camera world system. So yeah, the goal of the single-step progressive mapping is express the pose of multiple objects in the same coordinate system. So given the input feature of the image as xi, there is model n that predicts alpha, and with some assists, ijk is a location of the object, you can convert them to the pose information. So like this n is a CNN-based model, and it's used to map the local instant appearance to allocentric pose, to this allocentric pose like alpha I, and then using the coordinate system, we can convert it to the camera coordinate system. And in this paper, they argue that this is not necessary, so they just they use they propose this formulation, which learns intermediary features and then get the pose information directly without any assist. So they assume that this mapping to be progressive process, so that the mapping between the image and the pose is progressive process, and they in between they extract the IGRs gradually, and then the final result is the 3D orientation problem. So given the crop patch of one detected instance, The egonet predicts the egocentric pose as below. So here, H detects the heat maps for that instance. And then the function C maps those heat maps into key points or bounding boxes. Okay, so here is the architecture of the egonet. So here, as you can see, there is a function H. This one is the output of this function is the heat maps, and then you give this heat map to the function C, and you get the kind of 2D key points, and then you apply some affine transformation to the key points, and then from these key points, you can get the 3D information. Okay, we give example about this later. So, and also they say that you cannot assume everything as an intermediary geometric representations. So they define IGRs to follow these three properties, the availability. So the IGR should be easily driven from existing ground truth annotation with none or minimal extra manual effort. So like, for example, when the given bounding box annotation only, they define IGRs as a set of points on the bounding box with fixed ratio. And also discriminative, the IGR should be indicative for 3D pose estimation so that it can serve as a good bridge between visual appearance input and geometric target. And then transparency, the IGR should be easy to understand, which makes it debugging friendly and trustworthy for application. Yeah, so the IGRs that you define, they should be easy to derive from the already annotated ground truth annotations, and also it should be easily manipulated so that it will be debugging friendly. So yeah, so with this in mind, like for a given 3D bounding box for each instance, they define their IGRs as this cube with interpolated points around the edges. So how do they get the edges? So each given 3D bounding box, they have 12 lines, and they are denoted as, and each line is denoted with starting point and the ending point. So for each cube, we have like 8 endpoints, and we have a centroid. So the total of 9 points. And this 12Q means we have 12 lines, we have Q number of points on each line. In this case, we take Q as a 2. So there is 2 points on the line. But we don't predict the translation. We only predict the orientation of the object in the egonet phrase. So like in this phrase, it only predicts the orientation, and the translation is done in the upper part. So since we don't need to do the translations, then we don't need the centroid. So we just remove the centroid. So now we have 8 plus 12 Q points for our IGR. And yeah, so given the vertex of each cuboid, we can define these points on the line through this formula using the interpolated matrix. So there is a little bit math involved behind this, which will take some time to explain it. So I'll just go through it. So yeah, so when given the edge of the point, you can easily define the location of these interpolated points along the edge easily. And you can increase the number of the points, like you can take Q as a 3, 4, or 5, but it will be a little bit high computational. So they just took Q as a 2 equal to 2, and this worked fine. So the IGR is a set of the points, and then they remove the translations. So this is the final what they want to predict from the given instance. And yeah, so the given camera intrinsics, we just transform them into camera coordinates and we get the final output. And also they argue that, like, in summary of this section is that the IGS can be computed with zero or extra manual annotation and are easy to understand and contain rich information. Yeah, so this, when we detect these points on the bounding box, it's very useful for detecting the orientation of the instance. And since we already have the bounding box annotation for each instance, detecting these, annotating these points are not that hard, actually. It just needs some math formula. And also, yeah, there is more math involved here. So when given 4 points, no matter how you project it, like you project it, like this is a 3D, and when you project it into image plane, this will be the final shape, but the cross ratio for these 4 points is always the same. Like if there is 4 points, the cross ratio is always 4/3. So cross ratio can be defined as this. This V is a location of the points. So with this in mind, they proposed this loss, cross ratio loss, and they calculate, first they, given the bounding box, they calculate the cross ratio, the ground truth cross ratio, and then after the prediction, when the model predicts these 4 points, let's say for this edge, then you can use this L1 loss to penalize if any points is not correct. So like this loss can help for self-supervising. And also, yeah, so for cross ratio loss, we do not require any ground truth information, which means that unlabeled vehicles instance can be used to supervise the learning of this IGR, the final interpolated cuboid. So in addition, the preservation of cross ratio holds irrespective of the camera entry as long as the center projection model is used. So this center projection model is usually used for projecting the detected 3D into image plane. Yeah, so this is what we detect in 3D world, and this is what we visualize it after projection. So as long as we use this center projection model, we can apply this cross ratio loss in any data that detected with different camera or different environments. So here is the forward pass of the EGONET. So as an input, it can take the labeled data in this format and then also unlabeled data. And it has 4 type of loss for heat maps, cross ratio, 2D and 3D. And then the final loss is a summation of the all losses. And also while training, if we have the ground truth annotation for instance, we just penalize the model using all the losses. But when we don't have the ground truth annotation, then we just penalize only the cross ratio loss. So here is the results. So the blue dots are ground truths and the red dots are detected bounding box, detected IGRs for each instance. So for this upper part, we can see results and the ground truth, but this lower part is on the unlabeled data. So yeah, for evaluation, they use the Kitty dataset for 3D object detection, and there are some information about the Kitty dataset. And then for evaluation metrics, they use average orientation similarity. And also in average orientation similarity, it has 3 levels: easy, moderate, and hard. So easy is the instance that are closer and not occluded, and moderate is a little bit far or sometimes occluded one, and the hard one is usually the instance that are very far or occluded by other cars. So like this one probably is easy part because it's not occluded, but this car behind maybe it's moderate because it's occluded. partially occluded by this car. And there is no hard example here. And yeah, so there is some ablation study about direct regression and the learning with IGRs. So direct regression is a method that they just directly regress the 3D information from the images, and learning IGRs is what Egonet proposes. So like in this model, you can see this method B, like it has 95, this is the values of evaluation. And here they assume that the 2D detection is 100%. So when you add IGRs to this model, the accuracy increased a lot. And also they say that the accuracy of the model when we add IGR is bounded by this 2D detection. So if the model is like if they do 100% 2D detection, then when we add IGRs, the orientation detection can also be up to 100. Okay. So this is the evaluation with other state-of-the-art models. And as you can see, the Egonet outperformed the state-of-the-art by a lot in all metrics: average, moderate, hard, and easy. And also you can add Egonet as a module. For example, this module CVPR, so this at 3DP is 2D detection of the like so here the 2D average precision of the detector. So like the usually 2D average detection for these two models is 92 and 90, but when we want to detect the orientation, the accuracy drops. But when we add Egonet, the accuracy almost climbs up to 2D. And it cannot outperform the 2D, but it can go up to 2D, which is huge improvement according when we don't have Egonet in them. So Egonet also can be used as a model. And also there is some evaluation as a bird eye view. As you can see, the Egonet is much closer to the ground truth than any other models. So yeah, this kind of summarizes the benefits of using intermediary geometric representation for getting the 3D information from RGB image. Yeah, that's all.